Welcome to Introduction to Statistics in AP Biology. We use statistics a lot in biology in order to look at data, make inferences about it. So let's get started. So scientists typically collect data on a sample of a population. We use it to infer what is happening in the general population itself. So unfortunately, statistics, we can't, if we're looking to survey every human on the planet, it would be kind of insane. So we collect it in a sample. And by looking at that sample, we assume that that is representative of what the whole population is. So the first step in analysis and analyzing that data is to graph the data and examine the distribution. So the distribution typically will show typical data, shows a normal distribution. We call this a bell curve shape. It's like that because it's kind of curved like this. It looks like a bell. And right in the middle, we have our mean, our average, and then everything kind of falls away either above or below the average there. So this is what we are looking for in normally distributed data. Central tendencies are things that we use to describe statistics. It allows researchers to describe and quantify differences between data sets. So when I quantify something, I am able to reduce it down to a number and kind of make inferences based on that. You guys have done this before, even though we're calling it something different. We're calling it the measurements of central tendencies. It's really the mean, the median, and the mode of a group of numbers. These together are called the central tendencies. So mean is the average of a data set. Down here you can see some, are they going to give you the numbers? Okay, not. You can see there are some symbols here. These are equations you're going to be given in your equation sheet for your exam, but essentially X with a line over it is your mean. It's your average of your data set. This is one point in a data set. This is another point. This is another point, all the way down to however many points we have. And we're going to add all of those up and divide by the total number of points. So let's say here we have 1, 2, 3, 4 points. Our n down here would be 4. Okay, so it's adding them up and dividing them by the total. So let's practice. A student in biology class planted 5 tomato seeds in separate containers. They exposed the seeds to an artificial light source for 20 days. At the end of the 20 days, the students measured the height of the tomato plant that grew from those seeds. Here's the data. So we have 5 plants, 1, 2, 3, 4, 5, and we have their height measured in millimeters, 65, 52, 71, 56, 61. So what is the mean of the data? I'll give you a minute to go ahead and calculate that. You can pause it here. I'm going to calculate it as well. So how I do this is I'm going to do 65 plus 52 plus 71 all the way down. So 65 plus 52 plus 71 plus 56 plus 61 is 304. So when I add all of those heights up, it's 304 millimeters. We're going to want to keep our unit straight. Then we're going to take 304 and we're going to divide it by the number of total plants. So we have 5 total plants. So the mean of this data set, and do they give us the answer? Yes, they do. The mean of this data set comes out to be 60.8 millimeters. You guys want to see if I'm right? I know that we haven't officially met each other yet, but I am very bad at math. You're going to see this. So, well, it's important to know our limitations. So the first step, add all of the data points together. So we got 65, 52, 71, 56, 61. We added them together. We got 305. Then we're going to divide by the sum by the number of data points. Again, we have 5 data points. We planted 5 plants. So we'll do 305 divided by 5. I got 61.8 or 60.8. They rounded up. No big deal. The mean for the sample of 5 plants is 61. So that's how you would say it in words. Okay? Pretty straightforward, pretty easy. It's getting an average of something. So how does this apply to the general population? This is the next step in this question, is talking about, so we got this number of 61. Great, love it, no big deal. But how does this apply to the general population? This means that if the students went out and collected hundreds of samples of tomato plants growing under these exact same conditions, and we graphed the data, they should find the center of distribution to be around 61 millimeters. So if we're looking at our bell curve like this, 61 millimeters is going to be right in the middle. That's going to be around the average. Everything else is going to be distributed either above or below. Okay, let's talk about medians. Median is the middle number in a range of data points. In order to solve this, first we have to arrange the data points in numerical order, and the middle is the median. The middle number in that set is the median. If there is an even number of data points, so if there's no actual true middle, you average the two middle numbers. It's useful in data sets that have measurements with extreme values, right? Or this is considered an abnormal distribution. Is, let's say we have, we took the full set of numbers of, exams out of 10. So one person got a 1, a bunch of people got 5s, a bunch of other people got 7s, 3, 4, and a few people got 10s. This 10 and this 1 are your outliers. Those are your extreme values. So getting the median number kind of gives you a good idea of, what the middle is, right? Instead of getting an average. So median is not distorted by big or small numbers. So in our former example, when there's a bunch of 5s and a bunch of 7s and there's that 1, that 1's going to throw everything off. You guys already know this because looking at your grades, if someone puts a 0 in your grade book, it tanks your grade, right? That's because that 0 is an extreme value. Okay, it works the opposite way too, is that if someone puts in 100 in your grade book, it's going to skyrocket it, right? So we use this because the median is not distorted by those extremes. So let's practice. A group of Labrador retrievers is training for the police academy. Oh, how cute. One test is the sniff test, where police officers time how long it takes the dogs to find a scent. They collected the data on a group of 9 dogs. Here's the data. Okay, so we have 9 different dogs, and we have our time in seconds. So already, right off the bat, you can see there's a 21, which is kind of a small number compared to like 180, right? So these are a data set with extreme values in it. The best one that we can, the best central tendency that we can use to describe this data is the median. So first step, arrange the number in numerical order from lowest to highest. So here it is. 21 is the lowest, 180 is the highest, everything else is in between. Now, how I like to do this, step 2 is just find the middle value, is I go through and I start crossing them off. So cross off this one, cross off this, 2, 2, 3, 3, 4, 4, and we're left with this in the middle. Okay, so 48 is that middle value. All right, so the median is 48. The mean, if we were to get the average of this, is 69.9, which is a little bit higher than the median because of those extreme low and high value sets. So the median is actually a better measure of how to describe this data, right? If we take the average just kind of blows that mean out of the water, or blows that median out of the water, right? So the median is a better measure here to describe the data, right? And you can kind of think of it like this. The mean of 69.9 would be somewhere in here. Look at how many numbers it leaves out, right? Great. So median's a better measure in this data set. All right, let's talk about the mode. The mode is the value that appears the most often. It's useful when describing distributions of data where the mean and the median wouldn't be appropriate. So you would really use the mode as a last resort. It's not usually used as central tendency. An example of this is bimodal distribution. We're going to get into this a lot when we get into natural selection and ecology, where we're seeing a lot of individuals who are distributed on one side and individuals distributed on another. A good example of this could be like number of sexual dimorphism in peacock species, right? So males are going to have males would be up here. Males are going to have like a lot of feathers and females wouldn't, but there's not so much in the middle here. All right, we can call this disruptive selection. We'll get there. That's unit 7. Don't worry. Okay, let's do a quick review. What are the 3 measures of central tendency? Take a minute, write it in your notebook. Pause if you need to. And if you said mean, median, and mode, you would be correct. Which measure of central tendency is best for data sets that have abnormal values, extreme highs and lows, and why? It's one of these 3. Pause if you want to write that down. I'm going to show the answer in just a sec. 1 sec. Great. Median. Median is the answer here. It is not distorted by those big values, right? Okay, practice problem. And I think that this, we'll do this together. So it reads, researchers are interested in how long students spend on TikTok app per day. They take a random sample of 10 high school students who use an iPhone. They examine the amount of time each student spends on TikTok by looking at their screen time for 1 whole day. Here is the data. Oh my goodness, student 8. It's a lot of time on TikTok. For this data, determine the mean, the median, and the mode. Then identify which measure of central tendency would be most accurate for this data set. So here's our data. Our mean here you would get by adding this all up. So 10 plus 55 plus 85 plus 25, 44 plus 37 plus 42 plus 201 plus 56 plus 59, and we're going to get a number. Once we get this number, we're going to divide it by the total number of students, which in this case is 10. Okay? So the mean here is going to be, this is the average, 61.4. So I imagine that this number here is 614, right? Because you divide that by 10, you move the decimal. Awesome. So that's how we would get our mean. We would add them all up and divide them. Our median, first we would need to put these numbers in order. So we do 10, then there's 25. My numbers are kind of close together. Then 37, great. 42, awesome. 44, great. 55, I'm gonna run out of room. 56, 59, just gonna continue down here, 85, and 201. Okay, so now that I have them in numerical order, I'm going to start crossing them out. So 10, 201, done. So that's 1, here's 2, here's 3, here's 4, and you see we have an even number. So how would you find the median if you have 2 numbers in the middle? Well, you would add them, 44 plus 55. And you would divide them by 2. In this case, your median is going to be 49.5. So let me just double check that math. 55 divided by 2, 49.5 is your median. And what is your mode? What is the number that appears the most? Trick question, there is no mode. That's okay. There doesn't have to be a mode. Every number can just appear once. NBD, no big deal. Okay? So that's your mean, your median, and your mode. In this case, the best measure of central tendency would be the median. Because honestly, it's because of student number 8. Look at that outlier. That's insane, right? If number 8 wasn't in this data set, I would say that the mean is probably the best way to describe this data. But because of this outlier, you're going to want to use the median. It's a better representative number of what's going on up here. Okay? So sometimes when they're asking you what is the best measure of central tendency, sometimes you have to do all 3 and then look at it and just sort of judge. and be like, okay, 49.5 is a lot closer to most of these numbers than 61.4, right? Cool. So variability within a data set, really important. So measure variability is how far a data set diverges from those central tendencies. So how spread out the data points are. We measure this by two metrics. One of them is a range, and one of them is a standard deviation. So range is just the difference between the largest and smallest values. A larger range indicates a greater spread of data. Do they give me an example? They don't. Okay. So for example, if, well, let's go back, right? So taking a look at these numbers here, the students and the amount of time that they spend on TikTok, the lowest number is 10 and the highest number is 201. If I take 201 and subtract 10, let's see. I need a calculator for this. I am not great at math. All right, 191. So the range is 191. That's a huge range, right? So it's between the largest and smallest, and it's a huge spread. So larger range means greater variability. So there's way more variability between each data point than not. If it's a smaller range, like let's say all of these students spent, you know, this one spent 60 minutes and this one spent 62 minutes and this one spent 58 minutes, right? If it's a smaller range, then it's going to have less variability within it. Okay. We use range in conjunction with standard deviation. And we're going to get to standard deviation in just a sec, but we use the range with the standard deviation to make inferences about data sets. So, oh, they want to use tomato plants. Okay, so we're looking back at this data for the tomato plants. What would the range be? So I see here the lowest number is 52 and the largest number is 71. So we're going to do 71 minus 52. And again, I'm using a calculator because that's what I do. All right, so our range is 19. Okay, not a bad range. Let's see if they gave us that. Yep. So smallest number, or largest number, subtract smallest number. And you get your range. If you do it the opposite, no big deal. It'll just come out to a negative number, and then you'll just say to yourself, like, oh, I subtracted the wrong number from the wrong number. Right? All of these ranges should be positive. Okay, so that's range. Awesome. So standard deviation. This is a measure of how spread out the data is from the mean. So remember the first chart that we saw, and it kind of looked like this. This is the bell curve. So you have your mean right in the middle, and the standard deviation is how far out from the mean this data goes. So low standard deviation means that the data is closer to the mean. So going back to this chart here, if you have a low standard deviation, it looks something like this. If you have a high standard deviation, it's more spread out. If you have a low standard deviation, that means that your independent variable, the variable that you are changing, is causing the changes we see in the dependent variable. This is good. We want low standard deviation because that means that the thing that we are doing in the experiment is the thing that's causing the change that we see. That's great. You have low standard deviation. Beautiful. High standard deviation, not necessarily bad, but we don't really want to see it with accurate data sets. It means that the data is further spread out from the mean. So again, it kind of looks like that as opposed to up and down like that. Okay, so it's more spread out. When you have a data set where you have a high standard deviation, that means that there's something else going on other than the independent variable. So, and I'm sure they're going to give you examples, but for example, just off the top of my head, if you're trying to do an experiment of, if I change the temperature in this enzyme, it's going to increase the rate of reaction. If I do that 100 times and I have a high standard deviation on that, that means that the temperature, the thing that I'm changing, isn't the thing that's causing the enzyme to do what it's doing. That might be a little confusing. We're going to get into it. Let's dig into it. So again, high standard deviation means low to the ground. Low standard deviation means high up in the air. Okay? So you can see this dotted line is your mean, and everything that's close to the mean on either side, low standard deviation. If it's further away from the mean on either side, we're going to see high standard deviation. It deviates from the norm. If I say you are deviating from something, that means that you're moving away from it, right? So deviation, standard deviation. If it's high, that means there's a lot. If it's low, it means there's little. Okay. This is the thing with standard deviation that like scientists are all crazy about. One standard deviation from the mean represents 68% of all of your data. We're going to see this visually in just a second. I'm just saying it in words now, so bear with. Okay, 2 standard deviations from the mean will include 95% of all of your data points. 3 standard deviations from the mean includes 99% of all of your data points. So this is sort of how we use it to describe how certain we are that the results that we are seeing are a result of something we changed. So here's what it looks like. Here is your mean. And are they going to do? Yep, there we go. Your mean's right in the middle. And plus or minus 1 standard deviation, that's what we call it. Right down here, this is what we use. That's minus 1 standard deviation. That's plus 1 standard deviation. That means mean. 68% of your data should fall in this category, right? So it should be right in through here. That's 68% of your data. 95% of your data should fall between 2 standard deviations of the mean. So again, here's 1 standard deviation plus, 1 standard deviation minus, then you have 2 standard deviation minus, 2 standard deviation plus. Okay, so this right here, 95% of your data. Moving one more out, 99% of your data should fall within 3 standard deviations of the mean. So right here and right here, this should be 99% of your data. Okay? So that's just how we talk about it. And you'll hear scientists say like, oh, we got this number plus 1 standard deviation, right? That means that they got a number that lies right here plus 1 right over here. So the data that the scientist is referring to when they say plus 1 standard deviation falls right over here. Okay? It's just a way that we talk about numbers. It's a way that we talk about data. Here is the equation for it. Now, you're never going to have to memorize these equations. They will give them to you, both on the exam, on my exams, on the exam in class, on the College Board final, everything, okay? So don't feel like that you have to know this. But it is important to know what these symbols mean. N meaning number, X meaning data point, this meaning sum, right? This is your mean, okay? So we're going to practice these. I just want you to get familiar with this equation. So here's your formula. S stands for standard deviation. Sometimes you'll see it as SD, or most of the time you'll see it as S or SD. This right over here is sum of, right? So the standard deviation is the sum of a single measured value minus the mean squared. Okay? So when we do this, like in class together, when we do this on practice problems or whatever, the first thing that you're going to do is take your measured value and subtract the mean from it. You'll do that for each data point. You'll square it and then add them all together. Now, down over here, this n minus 1, we call this degrees of freedom. We're going to see degrees of freedom used throughout the year. Truthfully, not a clue what it's supposed to mathematically mean, but it's just something you have to memorize. It is the number of categories minus 1. Don't ask me why. I don't know. Math just maths out that way. Okay, so when I say, oh, it has, what's your standard deviation? It's going to be the number of trials minus 1. There are 4 steps to solve this problem. first, you got to find the mean. Next, you have to determine the deviation from the mean for each data point and square it. So that's this portion right here. So there's your mean. There's your data point. You're going to find the difference and square it. Then you're going to calculate your degrees of freedom, where n is the number of data values. So for our 9 dogs in our previous example, that were sniffer dogs or whatever, our degrees of freedom is going to be 9 minus 1, so it'll be 8. Then you put it all together. So here we go. We're back to our tomato plants. Here's our plants. We have 5 of them. Here's our height values. Awesome. So we're going to use this data from our tomato plant experiment. So first we're going to find the mean, and we do that by adding up all the values. Comes to 305 divided by the number of data points. And again, they rounded up. It's actually 60.8, but it doesn't matter. So 61. A lot of times we're going to set up charts, right? Some of these larger statistical analyses are better when you look at it in chart form. So remember our mean, which is x, line over it is 61. Okay, so we're going to determine the deviation from each point and square it. It's helpful to use a table. So we have our value, which is our x, and then our mean, which is 61. And that equals 4. Then we're going to square it. Okay? And we're going to do that for all of them. Don't worry if you get negative numbers here, because when you square them, it becomes positive. Great. So we're just doing the same thing. We're doing the x value, which is the data point that we got. We're doing the mean, and then we're going to square it. Okay? And we do that for everything. So here's what we got. Here's what we got. The next is we have to determine our degrees of freedom. This is step 3. Our degrees of freedom is the number of data points minus 1. In this one, we have 1, 2, 3, 4, 5, minus 1 equals 4. Step 4, you put it all together. So the first thing you're going to do, this column right here is this value. The degrees of freedom down here we know is 4. So now you're going to sum all of these values. So first you're going to sum. 16 plus 81 plus 100 plus 25 plus 0 is 222. So that takes care of your numerator. Now we're going to take 222, which is our numerator here, and we're going to divide it by our degrees of freedom, which is 4. After, I should say, before we get there, you're going to square root the whole thing. So however, order of operations, you remember that from algebra, 222 divided by 4, square root. Our degrees of freedom is 7.45. I'm sorry, not our degrees of freedom. Geez, our standard deviation is 7.45. Okay? So I know it sounds like a lot. It's a lot of math. Remember, this is our statistics unit, so there's going to be a lot of math. But if you take it step by step, kind of do this. X value minus mean squared. Add them up. I'm going to add this whole thing. All right? And then just plug it in. It's a plug and play at that point. Okay, so, but what does this all mean? What does it mean? So we have our mean. This is our average, 61 millimeters. And we have our standard deviation of 7.45. That means that one standard deviation from the mean should be plus or minus 7.45. Which means, if we're making our graph, right, and we have our 61 here, one standard deviation out is going to be 68.45. And one standard deviation back is going to be 53.55. So it's plus or minus, right? It's give or take. So that's one standard deviation out. 68% of all data should fall between 53.55 and 68.45 millimeters. If our if our data is normal. If what we're seeing is a result of the thing that we changed, that's what we're going to see. In 2 standard deviations, you just take this and then times it by 2. Okay? So 2 standard deviations from the mean of 61 is going to be plus or minus 14.9 millimeters. So 95% of our data should fall between 46.1 and 75.9. That's what that means. For 3 standard deviations, you guessed it, we're going to be taking our regular standard deviation and timesing it by 3. Okay, so we get 22.35 standard deviations from our mean, which means that 99% of our data should fall between 38.65 and 83.35. And this is a way, do we get into it? No, we don't. This is a way that we can talk about our data as confidence levels. So this is all data based on tomato plants, right? The height of tomato plants that were grown. If we went out into the real world and we started measuring tomato plants that were under the same conditions as our experimental conditions, almost all of them would be between 38.65 and 83.35. If we see something less than this in our data, or something greater than this in our data, there's something else going on. We don't know what. Maybe the plant got less sunlight or less water or less nutrients or whatever. But at that point, when we see that, we have to take a step back and go, okay, what's going on? Here's some YouTube videos. I will drop these online. You can watch them in your own time. Okay, standard error is a little bit different than standard deviation. Standard error of the mean, sometimes written SEM or SE with the sub X here. I know it says X. It's used to determine the precision and confidence in the mean value. So we have our mean. How do we know if that's a valid data point? How well does the mean of this sample represent the true mean of the population? Remember the very first slide that we talked about here. It's that we use statistics with samples of populations, but how well does this really match up with what's going on in the real world? It's based on a few things. First, it's based on your standard deviation, how variable from the mean we are. The next, it's based on the number of data points. The more data points, the more confident you can be in your values. If you have a low standard error, it increases the confidence. So if there's a low chance of error, that means that there's a greater chance that this is what we're seeing in real world. It's commonly given as this. So we're going to see plus or minus some number and then SE. Here's how we figure it out. And you can see here why your standard deviation value is so important, doing that math correctly, because you put your standard deviation up top, the sample size, so the number of trials in our tomato plant, this was 5, tomato plant experiment. With the dog experiment, it was 9, right? So it's just the size of the sample. And you square root it. And again, it's just a plug and play. So here's the formula. Don't freak out. You're going to get these formulas. But you can see S is standard, E is error, X with the line over it is mean. Standard error of the mean. Okay, let's practice. Going back to these tomato plants. So your standard deviation we figured out is 7.45. Our sample size is 5. At this point, it's really easy. You just plug it in and you solve. So I would do it first by getting the square root of 5, taking that number, 7.45 divided by whatever the square root of 5 is. So your standard error of the mean here is going to be 3.3. This means that each measurement varies by 3.3 from the mean. So again, this is a plus or minus. This is a give or take. What that means is that in this plant, in this single plant, each measurement varies. So it could be up or down from the mean itself. This is how we represent it. And I promise you, you're going to be so annoyed with this because we do this all throughout the year. How we add standard error bars to graphs. So we would first plot the mean, which is 61, Then we would go up by 3.3 and we put a line. Then we go down by 3.3, put a line, and connect those lines. That is your standard error. So up top is going to be the higher of that. So you do 61.1 plus 33.3 for that top line. The bottom line, it would be 61 minus 3.33 for that bottom line. And then you just connect them. What this means is that anywhere that the data falls, essentially from here down, is valid data. We have a little wiggle room, plus or minus, give or take. Again, I'm going to post this on Classrooms. You can watch it in your own time. So let's take a look at what we can do with this information. After we have it, we graph it, we put our standard deviations, we have our standard errors, we have our error bars. What do we mean? If error bars overlap, the difference isn't significant, right? So if they do overlap, it may be significant. So notice for each one of these trials, your error bars overlap, right? This tells us that the difference that we see isn't significant, right? So in this particular trial, you have error bars and they overlap. They overlap right here, okay? That means that it's not a significant difference. The difference that we see in those two trials, not a big deal, right? That is, we can ignore that, not a big deal. But if they do not overlap, it might be a really significant difference. Okay, so let's say that, this is the last slide, as you can tell. Let's say that this error bar was here, like this. Well, it probably wouldn't be up that high if it's down that low. Right, so it would probably be like this. In this case, these error bars don't overlap at all. That means that there's a significant difference between that data. We got to go back to the drawing board. Okay, so that is a crash course in statistics for AP Bio. Your notes are done. If you did this lecture video second, you are done with summer work, and I can't wait to see you in class. All right, I'll see you soon.